Hi, my name is Donalek, and this is the second lecture in the series Introduction to Machine Learning. In the first lecture, we have defined machine learning, data mining, and KDD, and the problems that can be addressed with these techniques. In this lecture, I will focus on supervised learning. Now, today, I'll start giving a more formal definition on supervised learning, talk about how to create a proper training set, the steps involved in the learning, and we'll see what it is and how to avoid overfitting, focusing on cross-validation techniques. Now, as we have seen in the previous lecture, we talk about supervised learning when, for some examples, the correct results are known and are given an input to the model during the learning process. Basically, the training data set includes input data and response values, and ideally, the algorithm will be able to generalize, meaning it will be able to determine the correct results also for unseen instances. Last time, we have also seen the most common tasks in data mining. Just as a reminder, for supervised models are classification, regression, and prediction. And we talk about classification when we have categorical outputs, and data can be separated in specific classes, while in regression, we deal with continuous outputs. Now, let's define supervised learning more formally. The training data consists of a set of training examples, X, and corresponding known outputs, Y. X is an n-dimensional feature vector, while let's suppose Y is a single target value. As an example, let's consider a bank that wants to come out with a credit formula to give or deny a credit to their customers using historical records. In this case, the input data are the customer application forms with fields like age, gender, annual salary, current debt, and these are all fields related to the credit score somehow. And the output will be a binary output, accept or deny the request, so basically +1 or -1. After that, there is the ideal target function that maps X into Y. It is unknown, and it is what we want to learn. In fact, of course, if you already knew F, there will be no need for learning. We could apply that and be done. We see F only through the training examples. And in the case of the bank, F is the ideal credit approval formula. Now, our goal is to learn F. So we want to find the hypothesis G that best approximates F. While F is unknown, G is well known since we are creating it and lie in the same domain as F from X to Y. To learn, we are going to use historical records as described before, where we know how those customers turned out to be. Now, let's see what connects the training examples with the hypothesis G. And it's the learning algorithm. Basically, the learning algorithm takes the examples and come out, hopefully, with a reliable formula. Now, finally, we are going to add another component, the hypothesis set. What the learning algorithm does is to create the formula from a set of predefined functions. The set of hypotheses consists basically on the models we want to use. So it could be neural networks, simple vector machine, and so on. The hypothesis set is crucial because it tells us how we are going to learn, what we can learn, and so on. Learning algorithms and hypothesis sets are our solution tools, and together they define the learning model. For example, if the hypothesis set consists of a neural network, the learning algorithm may be the backpropagation. Now, let's see the steps involved in supervised learning and how they are related to the KDD diagram we have seen in the previous lecture. First of all, we need to define what data use as a learning set. For example, if we want to do an handwriting analysis, we need to choose if we want to use a single character or entire words. Then we need to prepare the training set that must be representative of all the eventualities we can cover. Then we need to transform the data, for example, extracting or selecting features in order to avoid the curse of dimensionality that will be covered in another series of lectures. Now, once we have our data, we need to choose the learning model. For example, neural network with a backpropagation learning algorithm. Choosing the right model is based on the task, speed of training, data available, and so on. For example, if we have many missing data, we know that some models can deal with missing data better than others. Then we need to choose a validation model, and we'll see shortly the different types. Then we need to start the training and compute the accuracy until we are satisfied with the results. Then we can finally freeze the model and use it to make the final predictions. Now, let's see these steps in more details. First of all, we need to create our training set. And that needs to be representative of the real-world data. In this step, we gather the input objects and the corresponding outputs. The outputs can come either from human experts or from measurement. This is a very crucial step because there is a very good say in data analysis, and it goes like garbage in, garbage out. Basically, your analysis is only as good as your data. If our data is not reliable, so will be our analysis. Then, to achieve better results, the model needs to be able to generalize, and to do so, we need to split our dataset in 3 independent sets: training, validation, and test set. The training set is a set of examples used in the learning phase where the target values are known. The goal of every learning algorithm is to build a model which makes accurate predictions on the training set. But be careful, because if we compute the accuracy on the same set, then doesn't give us a good indication about the generalization power of the model. And that's why we need a validation set. Now, the validation set is also used to fine-tune the architecture of a classifier and estimate the error. There are different approaches for selecting the training and validation sets. One simple approach is randomly select, say, 80% of the data for the training and 20% for the validation. This looks like a very simple approach, but has many downsides. The first is that you may be unlucky with the split and end up with the majority of the most difficult objects in just one set. So to avoid this, we can use cross-validation. Now, cross-validation techniques are used for assessing how the results of a statistical analysis will generalize to an independent dataset. We can use exhaustive cross-validation, which learn and test on all possible ways to divide the original sample, or non-exhaustive methods like the k-fold cross-validation. And let's see how this works. So first, if we want to use the k-fold cross-validation, first we randomly partition the original set in k subsamples. K can be 3, 5, or 10, depending on how much data we have and the purpose of the classification. Then, at each round, one subsample is retained for validation and the others for training. The process is then repeated k times, with each of the k subsamples used exactly once as validation data. At the end, we can average or combine the results to produce just a single estimation. The clear advantage of this method is that all observations are used for both training and validation, and each observation is used for validation just once. Now, another cross-validation method is the repeated random subsampling. At each step, we split the dataset in just two subsets, one for training, one for validation. Then we compute the validation error at each step and average over all the splits. Now, the advantage is that the proportion of the sets is not dependent on the number of the faults, while the clear disadvantage is that some samples may never be selected for validation or may be selected more than once in different splits. Leave one out cross-validation is instead an exhaustive method. We use just a single observation from the original sample as validation, and all the others are used as training. And this, of course, may be computationally expensive, especially if also the learning algorithm is computationally expensive, because we need to redo this process for the number of observations in the dataset. Now, we have talked about training and validation. Now let's see the final set, the test set. This is an independent set used only to assess the performance of a fully trained classifier, so it is never used in the learning process, and in that way it can provide an unbiased estimate of the generalization error. Now, a common problem in supervised models is the overfitting. It occurs when a model is not be able to generalize and start to memorize the training data instead of learning the general underlying trend. Okay, sometimes this happens because during the training we don't use the validation set, and that's why the cross-validation helps in avoid overfitting. Other methods to avoid overfitting involve regularization, early stopping, and we'll see them in more details when we'll talk about classification. Now, looking at the figure, which fitting model would you choose? Well, the first one is too simple. The third one is a clear case of overfitting, while the one in the middle is about right. Now, you could ask, why not choose the third one that almost connects all the points? Actually, the problem is that it connects all the points, meaning that its ability to generalize will be very poor, because the main questions we should always ask during the training is how well our model is going to perform with the future data drawn from the same distribution but not used during the learning. Now, let's see another case of overfitting. Suppose we are training our model and get the results shown in this plot. The training error is shown in blue, while the validation error is in red, and both are shown as a function of a number of training cycles. Now, if the validation error increases while the training error decreases, then most likely we are overfitting the data, because the best predictive model will be when the validation error has its global minimum. Now, in this lecture, we have formalized the supervised learning, see how to build proper training, validation, and test set, and how to avoid overfitting using cross-validation. In one of the next lectures, we'll see in details some classification models, like neural networks and KNN.